1 minus negative 1. That's it.
I'm afraid you lost me.
Let's go back.
I don't see how we... I see how we got to the square root 1 and then like that whole thing, and then we apply the S thing, whatever that's called, to everything.
The definite integral.
The definite integral.
Good.
But I don't see how we move from that to the step underneath it.
You mean from here, here?
Yes.
Using the fundamental theorem of calculus. Finding the antiderivative and evaluating it from A to B. So the property says that this is 1, which function prime is 1, x. I plugged in 1 minus negative 1, which is positive 1. So 1 plus 1 is 2. Same thing here. 1 minus negative 1, 2. The square root of 2. Is that better?
So we treat square root 2 like a constant?
But isn't it a constant? Does it depend on anyone?
No, but does 1.
And we have a property that says that the constant goes in front. And then I have to have something here. I cannot have 0 because 0 times the square root of 2 will be 0. So this becomes 1. Is that better?
Could you show the original problem one more time? Okay, thank you. So our goal was just to prove it?
That's it.
All right.
So we started like we always do. Then we are trying to slowly but surely build the function in the middle. I needed the x squared, which is between 0 and 1. Then I needed 1 plus x squared. And since these are increasing and all positive, I can apply the square root. And the integral from negative 1 to 1 from 1 is x. The square root of 2, the integral from negative 1 to 1 is x from negative 1 to 1. And when I evaluate this, I get 2. And when I evaluate this, I get 2 the square root of 2. Would you like to upload just this so I make sure that everything is clear with that? And then we can look at another proof. And then I would like to talk about how we evaluate definite integrals.
So is this 5 point anything, or is this just like...
This is 5.2. This is 5.2, the definite integral. But I don't wait, like we didn't wait with the L'Hopital's rule till chapter 4. We talked about it in chapter 3 because we were ready and it was necessary. The same thing here. I don't wait till 5.3 to present fundamental theorem of calculus. I needed it. There is no point in waiting. We have all the information we need. Do we need more time? Do we need more time?
Yes.
Okay. I'm gonna get water. Should we look at another property, a problem?
Yes.
Okay, perfect. Okay. Can we continue then? Okay. Okay, so let's take a look at 66. Same page, 397. The integral from 0 to 1, from the square root of 1 plus x squared dx. They want us to show this. So prove it. This we will be able to determine, but that we don't have, you have to wait till Calc 2 to determine that. Okay, so where is my starting point?
Would it be graph both of like the square root of 1 plus x and then the square root of 1 plus x
The
squared
starting
on the
point,
interval?
you could, but the starting point is between 0 and 1. That's our starting point. Okay, so for x between 0 and 1, which of these quantities, 1 plus x squared or 1 plus x, is smaller? This is very important. So the starting point is here. Yes, we could graph on the interval 0 to 1, but let's just think. Between 0 and 1, we can have 0.25, 0.5, 0.785, and so on and so forth. Any number between 0 and 1, when you square it, plus 1, will it be greater than 1 plus the number itself or less than? So take, for example, 0.5. When you square 0.5, you get a smaller number than the initial number, as long as the number is between 0 and 1. So which of these two will be smaller? This one or this one?
X squared?
Yes. Again, we are talking about numbers between 0 and 1. So any number between 0 and 1, when you square it, you will get a number smaller than the initial number. So therefore, this quantity is smaller than this. And as Katie said, why don't you graph? There is no need, but yes, you can graph. Good, but since these are positive and increasing, right? So in this case, also the square root will be smaller than this one. And I solved it. It's solved. So then the integral from 0 to 1, of course dx, don't forget dx. The integral from 0 to 1 dx is guaranteed. By what property? By this property. If a function is below another function, its area is smaller than this area. And that's exactly what this means.
So did we just completely ignore the 0 and multiply the x and the 1 by x plus 1?
We didn't multiply. We were just discussing that only when x is between 0 and 1, x squared will be a number less than or equal to x. That's why we started with that. That was our base of discussion. Only for numbers between 0 and 1, x squared is smaller than x. And therefore, 1 plus x squared is smaller than 1 plus x. Therefore, the square root of 1 plus x squared is smaller than the square of 1 plus x, and then the integral follows from the property. Is this okay?
So just to reiterate, when x squared is less than 1, it's less than x.
Only when x is between 0 and 1. When x is between 0 and 1, x squared is less than or equal to x. Is that better? Perfect. Okay, now I would like us to practice evaluating definite integrals. To evaluate, not showing, proving anything, but to evaluate definite integrals. And I like to start with one that I'd like to make up. So let's say the integral from -3 to 2 from 1 over x dx. What do I have to look at first?
Would it be the integral from 0 to 2 plus the integral from -3 to 0?
Very good point. So what you are really saying is that x cannot be 0, which means this function is not continuous on -3, 2. And the answer is FTC not applicable. Wait till Calc 2. FTC is not applicable if the function is not continuous on the given interval. The function is not continuous on the given interval because it's undefined at 0. So please remember, no matter what function you are given, or I should say not what definite integral you are given, you first have to check that this function is continuous on the given interval. If it isn't, that's the answer and you move on.
Is that the only thing we have to check? Like,
Yes.
I remember with like Rolle's theorem and stuff, we had to also check like
Yes.
there's different.
That's the only thing. Yes.
Okay.
Very good. Let me correct myself. That's the only thing. Also, if you have, let's say, a symmetric interval. So first you check that the function is continuous, and if you have a symmetric interval, then you check whether the function is odd or even. Only when the interval is symmetric. If the interval is not symmetric, like -3 to 2, you don't have to check anything. I mean the odd or even. But if the interval is symmetric, you will always check whether the function is odd or even. Is it odd or even? Which trig functions are odd?
Sine.
Yes. So odd trig functions. Anything that has sine in it. Sine x, tangent x, cotangent x, and cosecant x. Anything that has sine in it is odd. Anything that only has cosine in it is even. And there are only two. Cosine x and secant x. These are the only two even functions because they only have cosine in them. Any function that has sine, it's odd. Any trig function that has sine is odd. And there are only two even functions, the ones with cosine. And cosine alone. So then what is the answer?
0.
The answer is 0. Awesome. Thank you very much. Okay, so let's look at the integral from 0 to 1, and this is 47 on page 407. From, it says x to e plus e to x dx. They're asking us to find the definite integral from 0 to 1 from x to e plus e to x. Okay, so let's see how we determine what function prime is x to e. E is a number. What function prime is x to e?
x times
x to e to power e plus 1 over e plus 1 plus, which function prime is e to x?
e to the x.
That's it. From 0 to 1. When I plug in 1, I have 1 over e plus 1 plus e minus, preferably put parentheses. When I plug in 0, this piece is 0. But this piece is not 0. E to 0 is 1. So then I have 1 over e plus 1 plus e minus 1. Okay. What about 53? The integral from 0 to pi. Any questions? The integral from 0 to pi from f of x dx. And they're given us f of x as sine x for 0 to pi over 2 and cosine x for pi over 2 to pi. Okay. How do we think about this? What do we need to do?
Is it the or is it the theorem or law where we have to do a to
C plus C to, excellent. Yes, yes, yes. That's why I chose it, of course. So then the integral from 0 to pi from f of x dx will be exactly. So anyone would like to try?
would it be the integral from pi over 2 to 0 sine x?
But we
dx?
read from left to right. So from 0 to pi over 2
Okay.
from sine x plus
from pi to pi over 2.
I cannot
pi
read
over
from
2.
right to left.
Sorry, I did it again. From pi
So
over 2 to pi.
if we stopped at pi over 2, we have to start at pi over 2 to pi from cosine. Is this okay, everyone? We understand these steps?
Can you go through it one more time?
Yes. I see that pi over 2 is right between 0 and pi. The interval is 0 to pi, but I don't have a function that goes from 0 to pi. I have a function that goes from 0 to pi over 2, and a totally different function that goes from pi over 2 to pi. So the integral from 0 to pi over 2 is from function sine, and the integral from pi over 2 to pi is from function cosine.
Okay, I see.
Perfect. Which function prime? Yes, go ahead.
For this theorem, does it have to be halfway in between?
No,
Or can
it can be pi over 4. No, it can be any number. It doesn't matter. Which function prime is sine?
Negative cosine.
Very good. Negative cosine x from 0 to pi over 2. Plus, which function prime is cosine?
Is it negative or is it for the first one? Is it negative cosine?
When you
or I thought it was-
differentiate cosine, you get negative sign. You need a -1 to get the positive.
Oh, because it's the antiderivative.
Correct. Correct. Good. Which function prime is cosine?
Sine x.
Very good. From pi over 2 to pi. Good. Leave the negative outside, patiently waiting. Cosine pi over 2, that is 0. Minus When I plug in 0, I get 1. Plus, when I plug in pi, I get 0. Minus, when I plug in pi over 2, I get 1. So this is positive 1, and this is minus 1, so the area is 0. By chance. Okay. What about the integral from 1 to 9 of the square root of x dx?